Hello everyone, welcome back. Today we are continuing to explore how to apply machine learning to battery lifetime prediction. In our previous lectures, we went through how to make sense of battery lifetime data, how to perform feature engineering, and how to select models. Today, we are focusing on model interpretability. So we are going to go through together what is SHAP analysis and how to use it to explain battery prediction models. Let's dive in. So we've been talking about building a data-driven workflow for battery lifetime prediction. We take our data from typically the time series data of battery tests. We build our feature matrix, and then we train and test our machine learning models. We take the prediction outcomes as well as our models to apply them in a range of industry applications where batteries are used. So you may be asking, in our workflow, where does the explainability of our machine learning come in? So in a typical example of battery lifetime prediction using machine learning models, we are talking about building a black box model. In this example, we have the battery formation parameters, so such as the temperature, the charge currents, the voltage, the verification cycles, the rest times. These are all parameters we put in our battery formation process. And battery formation is the last step of battery manufacturing. So these different formation protocols would lead to a very diverse battery cycle life. In other words, formation as a manufacturing step would impact how long a battery would last and when it will fail. So we can build a pretty accurate model to take the early cycling information from batteries and predict when it would fail. But at this point, it's a black box model. The idea of using the explainable machine learning is to open up this black box and then understand which of the input features are most important and how these features impact its final prediction outcome. So how does it work? A very popular explainable machine learning techniques being used in the battery lifetime prediction application is the calculations of Shapley values. So Shapley values is a concept first originated from the corporate game theory back in 1953 by Lord Shapley. So the idea here is that it's a way to assign the credits or distribute the costs fairly among the players based on their contributions. So an example we can take is if we have 3 people going for lunch together, and we say they form a coalition. In this case, like they work together to contribute to the final value. In this case, it's the bill of the lunch they need to pay together. And to really figure out like how much each person should pay, depending on their different dish, is where like Shapley values come into play. So in order for us to figure out how much this first person, let's say player 1, should pay for his lunch, and we can think about of removing member 1 from the coalition and see how much is the bill with the rest of the 2 members. And this gives the idea of the marginal contribution of member 1. So in addition to consider the marginal contribution like this, we also need to consider, well, there are interacting factors among the players. So like the total amount of the contribution of player like 2 and 3 may not be simply the addition of the individual contributions, because like let's say like when player 2 is in the same coalition as player 3, it may have extra like contributions. So what Shapley values take into account is it takes the average of all the possible like coalitions and the contributions from like the member 1, and then we average it. So this is the way we can have a computation of the Shapley values for member 1. Similarly, we can compute the Shapley values which quantifies the contribution of the player 2 and 3 in a similar way. And let's fast forward to 2017. That's where we have here in University of Washington, two researchers, Lockburn and Lee. They start to expand on the Shapley values and had this idea of SHAP analysis. So Shapley additive explanations. So here we have a model agnostic method, which means the SHAP analysis would work for random forest, linear regression, and neural networks. So it's model agnostic. But the concept is the same in the way that we explain the individual predictions by assigning each feature a contribution value based on Shapley values. So here we have the X, which is the feature values of the individual features, and then we have our machine learning prediction outcomes, and then we can assign individual contributions from each of the features here instead of each of the players when we're talking about paying lunch. So how does SHAP analysis work in a real-life battery prediction task? So here is an example where we have different formation parameters ranging from temperature, the current, the voltage, the verification cycles, and the rest times. So these are all the parameters we can change during a formation process. And the formation is the last step of battery manufacturing. So with different formation protocols, we can extract different features from the early battery cycling data. In this case, the feature matrix is built from the diagnostic features from the standardized diagnostic tests during the aging tests. So the data from this example is taken from the research papers shown at the bottom of these slides for those who are interested in knowing more about the battery degradation mechanisms and battery formation. So the idea here is that we can build a predictive model. In this case, a tree model would work pretty well. A random forest model have the mean absolute percentage error of less than 10%, using the feature matrix we build as an input. So now let's try to interpret this model. So how SHAP works here is that we take all the features in our feature matrix. In fact, there are more than 80 different features used in this model. And it ranks from the most important to the least important features that impact the prediction outcome. So in this case, on the slide, you see the prediction outcome of one single battery. So in this case, this battery have the actual cycle life of a bit over 1,000 cycles, and our random forest model predict it to have over 930 cycles as its cycle life. So that's kind of a note to remember. The SHAP analysis, we are interpreting our models. So in the way we are interested in knowing which of the features out of the more than 80 features in our feature matrix impact the prediction outcome of the result of this 938 cycle life, where it comes from. So let's first think about the base in the ways the average. So the average cycle life of this database, the data we used to build our predictive model, is around 734. But this battery have a longer cycle life. And different features, in specifically the top 4 features, these are the names of the features, which are the mathematical formulations from the time series data from our raw data. But the idea here is that SHAP analysis tells us, so the first feature, by this feature being at the value of 0.005, it positively impacts the prediction outcome by over 136 cycles. Similarly, you see the next few features also positively impact the prediction outcome. And you can imagine some features may also negatively impact the prediction outcome. So SHAP analysis allow us to quantify what is the individual contributions to the predictive outcome in this way. Similarly, instead of just focusing on one battery cell, we can have a SHAP summary plot. In this case, all these individual features, I know with these long names we give, is really just to tell us how important individual features are. So the one on the top and most influential one to our prediction outcome. And also we see whether it negatively or positively impact the prediction outcome. In this case, each of the battery cell becomes a single point on the figure shown here in this summary plot. So you see this is very informative. In a way, it tells us the feature importance ranking. It tells us whether each feature impacts the prediction outcome negatively or positively. It also gives a quantification of how much the individual features have the impact on the model output. So it's really handy for us to understand how our predictive model behaves. With this in mind, we can also expand similar ideas of performing SHAP analysis to different kinds of battery lifetime prediction models. In this case, instead of the feature matrix, we can simply build a protocol model. In this case, the input of our machine learning model can be simply just the formation parameters. So these are the knobs we can tune during the formation. And we can immediately see how the 6 parameters during the formation impact the cycle life of batteries. So here in this summary plot, you can see the temperature would impact the cycle life of battery the most. This will give the advice in a way to help the battery engineers to consider changing parameters such as temperature during the design of their formation protocols. So you can see this is an example where we can have our explainable machine learning applied to different machine learning models, and then it can help us to gain insight of the model as well as to help us develop the optimization protocols for our next round of battery design. With this in mind, let's zoom back to really consider what's the impact of explaining our machine learning models. So we really care about how much we understand our prediction outcomes. So when we are building a data-driven workflow to predict battery lifetime, once we have our predictive model, if we really start to apply techniques such as SHAP analysis, it would help us, firstly, to go back to better understand how each features contribute to our model, and this will help us to improve our model in the feature selection process. At the same time, if our input are actually the knobs we can tune during battery manufacturing, it would help us to have an actionable item in the way we know how we can go to optimize our process in the physical world based on the interpretations of our predictions. On the other hand, by understanding how our model behave, also help us to gain physical insight from the models. For example, the features that turns out to be most influential in its cycle life prediction may be linked to the degradation mode and the mechanisms behind the observables we see. And this would help us to further understand how batteries degrade, and that leads to the knowledge generation. So in short, this is important for us to not only have very accurate machine learning models, but also we should pay attention and make efforts to understand how our models behave. With that, thank you very much for listening, and see you next time.